everyone, welcome to IIT-JAM Chemistry tutorial number 43, and this is the first part of lecture number 3 of the physical chemistry chapter solid state. In this part 1, the theoretical part of X-ray diffraction and Bragg's law will be discussed, and in part 2 of lecture number 3, the numerical problems will be discussed. So let's begin with X-ray crystallography. It's a tool used for analyzing crystal structures. This crystal is to be analyzed with the help of X-ray crystallography, this tool. So first of all, X-ray is being generated here in a X-ray tube, and then this X-ray, after having been generated, this is a combination of a range of wavelengths. So this is called a white X-ray. This white X-ray, when is allowed to pass through a particular crystal which absorbs most of the lines except one, then monochromatic X-ray line is produced. Now this monochromatic X-ray beam is allowed to fall or pass through the crystal which is going to be analyzed. This diffracts these X-rays, and this in the photographic plate this type of pictures is obtained. Or if you start from here to any direction, then their intensity change with respect to the change in glancing angle will be recorded, and by analyzing this, theta is the glancing angle, 2 theta is plotted intensity against intensity, or intensity is plotted against 2 theta, then in that case this type of XRD pictures are obtained, and after analyzing the you will have an idea about the structure of this crystal. So what is the geometry of this diffraction? Let's start with the term scattering first. Okay, so this is the nucleus, and this is the X-ray. These arrows are directing this as actually the direction of X-ray lines. Now at a particular point here, here and here, the phase of that wavelength is same. So this line is actually wavefront. When this wavefront is approaching towards this nucleus, then it falls on the electron, and then electron starts oscillating, and then further X-ray of the same wavelength is scattered throughout in all directions, and then the spherical wavefronts are obtained. So the nucleus of the atom of the lattice point does not interact with the X radiation due to its heavy mass. This is the nucleus, but around the nucleus there are electrons. So X-ray actually falls on the electrons, interact with the electrons, because it cannot interact with the nucleus, because nucleus is a heavier body. The electron around the nucleus actually interacts with the X-ray falling on it. The electron starts oscillating and radiates X-ray of same wavelength. That means this to this distance is 1 lambda, and here this to this distance also 1 lambda. But this wavefront is planar and this wavefront is spherical. Thus an atom becomes a point source of X radiation. So this atom becomes a point source of X radiation, from where X-ray is being scattered in all directions spherically. Now this X-rays, if you take the tangent of this X-ray, let's go to the previous page here. This is the phase of any particular wavelength, and this actually look at the movement of the cursor, up, crest and trough, crest and trough, crest and trough. Okay, so 1 lambda is actually imagined like this. So this point, the phase of the wavelength is same on the surface of this sphere. Now they will undergo constructive interference because they are in the same phase. Okay, fine. So tangent of each wavefront produced from the lattice points undergo constructive interference. You know all about this constructive interference. So this is a point source, this is a point source, this is a point source, this one and this one is the point source. So let us take, for example, this is a point source, and these are the wavefronts arising out from this point source. This is a wavefront, this is a wavefront. Okay, now this is the second point source in the right hand side, and this is the second point of source point in the left hand side. So it will also have some wavefronts spherical, this will also have some wavefronts spherical. Okay, and these arrows are the falling X-rays. This is the X-ray of the monochromatic beam coming out from the monochromatic beam. This X-ray is falling on this point, this X-ray is falling on this, on the electrons of this nucleus, this one is falling on the electrons around this nucleus, and so on. Now if you take the tangent at this point of this first wavefront after having completed 1 lambda, then this one's tangent at this point, this one's tangent at this point, okay, then this one and this one will undergo constructive interference, resulting in this thing. This line is resulted out from constructive interference. Okay, a single high intense line will be produced, and this line is called zero order diffraction. This is not now scattering. After scattering, then it will undergo constructive interference, then the final thing is called as diffraction. And zero order diffraction has no significance because it will go straight to the same direction. There is no angular change with the falling X-ray and diffracted X-ray. But if you take the tangent first of this first wavefront and tangent of the second wavefront to the adjacent, then this one will go constructive interference with this one, okay, or this one will go constructive interference with this one, okay. So this way, the first one, second one, first one, third one, the first one, second one produces the first order diffraction, the first one and third one produces second order diffraction. This way these angles will be determined depending upon the value of lambda, that is the X-ray, and also depending upon the distance between these 2 points, that is the lattice arrangement, one dimensional arrangement. So the most intense zero order diffraction occurs from the interference of the first tangent of each lattice point. If first tangent of one lattice point interferes with the second tangent of the next lattice point, third tangent further of the next lattice point, and so on, then the first order diffraction is obtained. That is, this is the first order diffraction, look, from which it is arranging out. The first wavefront of this one, okay, the second wavefront of this one, the third wavefront of this one, all these have same phase at this point, and this point. So as a result of constructive interference, this intense line is produced, but it will have a little bit lesser intensity than this one. Similarly, the second order diffraction will be further less intense, but they will have some angle, and if you move from here to here, then you will find at what gap the highly intense pulse is produced or signal is produced. Now Bragg equation. Suppose this is a one-dimensional lattice array, M prime, N prime. The falling X-ray starts here from X1 to A, then goes to X1 prime after diffraction. This second line with the same monochromatic beam is falling on this lattice point from the N prime line, then passes through C to X2 prime. This angle CAD is the glancing angle. So similarly, since this is 90 degree and this one also 90, that means if CAM prime is 90 degree and DAX1 is also 90 degree, then this one also is equal to theta, because this one is theta. CAD, if it is theta, then X1A M prime is also theta. The distance from this line to this line is actually the interplanar distance. It is D, and if it is D, AC is D, then if this is theta, then CD is actually D sine theta, because CD divided by AC is sine theta. Therefore CD is AC sine theta, and AC is nothing but D. Therefore CD is D sine theta. Okay, and here these lines are behaving as if the X-rays are getting reflected, but this is not reflection, this is diffraction. But if somehow you use the term reflection, then you must put the inverted commas, because this seems like as if it is reflecting, but this is diffraction, it is not reflection. So we have some HKL lattice planes. This is HKL lattice plane, MM prime, NN prime. etc., having interplanar distance DHKL. In short, it is written as D only. HKL is omitted. A monochromatic beam of parallel X radiation is incident on these lattice planes because X1A and X2BC, these two are parallel to each other. Ray X1 is incident along path X1A and is reflected back along path AX1. So it is coming from here, starting its journey, falling on A and coming back from A to X1 prime. Okay, this is AX1 prime. This is not comma, apostrophe. This is prime. Ray X2 is incident along path X2C and it is reflected back along path CX2 prime. So this one is coming here, then going here. Glancing angle, angle X1 AM, angle X1 AM. This is the glancing angle. Or X1 prime A M prime. This is the glancing angle. These angles are theta. Let us draw AB perpendicular to X2C. So this AB is perpendicular to this line X2C, and AD perpendicular to CX2 prime or X2 prime C. Since CX2 prime and AX1 prime are parallel, CX2 prime and AX1 prime, these two are parallel. Okay. Therefore, angle CAD is also theta. So this, if this is the glancing angle, then this is also the glancing angle theta, because the angle, this is 90 degree as well as this angle is also 90 degree. Okay. Though the path traveled by X1 is X1A X1 prime, and the this is divided into two parts, X1A plus A X1 prime, and path traveled by X2, it is X2 B C D X2. That means X2B plus BC plus CD plus DX2 prime. The path difference, what is the path difference? That means from here to here to here minus from here to here to here. It is X2C X2 prime minus X1A X1 prime. Okay. Now X2C X2 prime means X2B plus BC plus CD plus DX2 prime, and X1A X1 prime means XA plus AX1 prime. And here, after deducting, you get BC plus CD. Now BC and CD are same, equal distance, so this is also equal to 2CD, and CD means the interplanar distance D. So this is no, CD means not D, CD means D sin theta, as we have said. Actually AC is D, therefore CD is D sin theta. So this is D sin theta CD. Since it is 2CD, so it is 2D sin theta. Now it is considered that path travelled by X1 up to A is equal to the path travelled by X2 up to B. So what things we already had considered. And secondly, the path travelled by X1 from A to X1 prime is equal to the path travelled by X2 from T to X2 prime. Okay. These two already have been considered. Now wavelength of the X-ray is assumed to be lambda. The reflected rays would undergo constructive interference on the condition. What condition? The path difference must be equal to integral multiple of lambda, that is n lambda. So the condition is n lambda x 2d sin theta. N is order of reflection, and this is known as the Bragg equation. So that's all for this lecture. Thank you and have a nice day.